Today, we're going to go over some examples of groups. Let's do a recap of where we were in our last video. Last time we defined a group as a pair consisting of a set G and a binary operation we denoted by circle that satisfies four axioms. First, we wanted closure. That is, given two elements A and B, we wanted this product, a circle B, to also be in the set G. Next, we wanted associativity. This simply means given three elements, A, B, and C, that it doesn't really matter the order in which we take the first two. We can either pair off A and B and then apply with C, or we can first apply with A and then apply with the pairing of B and C. Associativity says there is an unambiguous way in which we can define A circle, B circle, C. Identity says that there should be an element E such that A circle E equals E circle A, which is equal to A for all A in the set. Such an element E we will call an identity. Next, we needed inverses. That means for every element A, there should exist at least one element B such that A circle B is equal to B circle A, which is our identity E. Such an element B we will call an inverse of A. Sometimes we need to study groups that have just a little bit more structure than this general set here. We say that a group is an abelian group if it satisfies a fifth axiom, namely A circle B is equal to B circle A for all elements A and B in the set G. Well, what are some examples satisfying all of these axioms? Well, let's start with a relatively simple example, and let's actually try to work through to see which of these five axioms holds to be true. Consider the set of rational numbers. Remember that we denoted this by Q, and it consists of elements that are ratios A over Q, B over Q, such that P and Q are integers, and we do not want the denominator Q to be 0. Now remember that to have a group, we need two things. We need a set, and we need a binary operation. So let's say that our binary operation is addition. That is, it takes two rational numbers, A and B, and it will return a third number, A plus B. Well, we know that the first axiom, closure, holds because if we add any two rational numbers, we find another rational number. Here you can see on the screen that if I have the quotient P over Q plus the quotient R over S, I can write it again as a quotient of two integers. That's the important statement to make sure that we have a rational number, that we always get back something that is the quotient of two integers. Next, axiom associativity holds because, well, there's some nasty algebra to check here, but you can check that parentheses A circle B, parentheses circle C, is equal to A circle, parentheses, B circle C. Axiom identity holds because I can choose the additive identity in this case as just the ratio 0 over 1. You can check that this ratio satisfies A circle E is equal to E circle A is equal to A for all rational numbers A. Next, axiom inverses holds because if we have a rational number P over Q, I can consider the new rational number negative P over Q, and this now would be the additive inverse. That's because A circle B is equal to B circle A is our identity, which we denoted above as E. But we actually get one more axiom that holds, axiom commutativity. This holds because you can check that A circle B is equal to B circle A for all A and B. That is, the order in which we add two rational numbers does not matter. Now, there really isn't anything special about the rational numbers here. We could have gone through a similar argument if I replaced Q with the real numbers R or the complex numbers C. So we can conclude that the rational numbers under addition, the real numbers under addition, and the complex numbers under addition are all examples of abelian groups. Let's try for another example. Let's consider the natural numbers. Remember here, we consider these to be the counting numbers, 0, 1, 2, 3, and so forth. Again, we need a binary operation, so let's just choose the same one as before, namely addition. Well, the first axiom, closure, holds because if we have any two non-negative numbers, then the sum is also a non-negative number. Axiom associativity also holds. We won't worry about showing that here, but trust us, it does. Axiom identity holds because we can choose 0 as a natural number. However, axiom inverses fails because the additive identity of the number 1, namely -1, is not a natural number. It is an integer, but it is not a natural number. Even axiom commutativity holds because it doesn't matter the order in which we add two natural numbers. So staring at this, we know that the set of natural numbers does not form a group because axiom inverses fails. But if we're willing to allow maybe negative integers, then we would see the axiom inverses holds. This allows us to conclude that the set of natural numbers under addition is not an abelian group. However, it is a commutative monoid. The set of integers under addition does form an abelian group. Let's try for some more examples. Let's consider the n-dimensional vector space over the real numbers, which in this case we can consider now vectors corresponding to this n-tuple x1 ... through xn, where of course each component x sub k is a real number. Let's again continue our binary operation to be addition. Axiom closure holds because we can add together any two n-dimensional vectors to find yet again another n-dimensional vector. This is simply vector addition. Axiom associativity holds. Axiom identity holds because we could actually choose our identity simply to be the 0 vector. It's that vector where we have 0 for all of the n entries. Axiom inverses holds because if we have a vector, call it x1 through xn, then the additive inverse is just the vector corresponding to -1 through -xn. Even axiom commutativity holds. And as before, there's really nothing special about the set of real numbers here. We can replace r with the rational numbers q or the complex numbers c. But we can actually go one step further. There really wasn't anything special about n-tuples here. We could have actually replaced an n-tuple with an m by n matrix, which means the set of m by n matrices over the rational numbers along with addition, or the set of m by n matrices over the real numbers under addition, or the set of m by n matrices over the complex numbers under addition is an abelian group. All three of these are examples of abelian groups. But what if we took a look at a small subset of these matrices and we changed the binary operation? Let's consider now 2 by 2 matrices over the complex numbers, but let's assume that they are invertible. What that means is we could take a look at a 2 by 2 matrix. In this case, this corresponds to the array A, B, C, and D. And to be invertible, one proves in a course in linear algebra that this is equivalent to saying that its determinant does not equal to 0. Recall that the determinant of a 2 by 2 matrix is AD minus BC. The binary operation that we'll choose in this case will just be matrix multiplication. Given two n by n matrices A and B, we can take their product to find another 2 by 2 matrix. Axiom closure holds because if you're given two 2 by 2 matrices that are invertible, their product is also invertible because of a certain product rule involving the determinant. The determinant of a product of matrices is the product of their determinants, So if both determinants have a non-zero matrix, then their product has a determinant that is non-zero. Also, axiom associativity holds. This is more because matrix multiplication is just the same thing as composition of linear transformations. Axiom identity holds because now we could actually choose the identity matrix as our identity element. If we simply multiply by the identity matrix, that doesn't change our matrix capital A. Even axiom inverses holds because if we have an invertible matrix, its inverse is also an invertible matrix. This one proves in a course in linear algebra. However, axiom commutativity fails. You can see here with a very specific example. But the idea is that matrix multiplication is not a commutative operation. The product A times B in general does not equal to the product B times A. Now, just like with the previous examples, there really isn't anything special here about the complex numbers. We can replace C with the rational numbers or the real numbers, and there isn't anything special with dealing with 2x2 matrices. We could have easily dealt with n by n matrices. So we're able to conclude that the collection of invertible n by n matrices over Q, or over R, or over C, all with respect to matrix multiplication, are groups which are not abelian. Now up to this point, we've looked at groups coming from linear algebra that have infinitely many elements. However, are there any groups that have only finitely many elements? Well, let's take a look at one last example. What we're going to do is look at polygons that have sides of equal length. These are what are called regular polygons. You can see here for the first small values of n that we have equilateral objects, such as an equilateral triangle, square, regular pentagon, and so on and so forth. And what we'd like to do is ask about the rigid rotations of such objects. That is, we want to take these objects, perhaps spin them around, flip them upside down, but do things in such a way that we're not allowed to break any edges or to snip apart any objects. We simply are allowed to pick it up off the screen, rotate it, and then set it back down in the original orientation. So there's a way we can write this mathematically. Let's consider the vertices of these n-gons, these regular polygons with n sides, and let's collect all of these vertices into a set that we'll call capital A. We want to discuss the symmetries of this regular polygon with n sides, that is, this regular n-gon. Now, we can't just say, take these n elements and permute them around, because if we did, that would be the equivalent of taking our regular n-gon, perhaps breaking the sides, and then rearranging them back together. We're not allowing ourselves to do that. For example, if there's an edge connecting vertices P1 and P2, then however we move things around, P1 still has to be connected to P2 at the end of the day. So let's denote the set D sub 2n as the set of symmetries of the regular n-gon. They're all of the different ways in which we can kind of spin things around, rotate things around, reflect even the sides and the edges. And let's let our circle here denote composition of functions. We have three statements to make. First, this set, along with this binary operation, is a group, and this group only has 2n elements. Second, this group actually can only be generated, is only generated by just two elements, namely a rotation by 2 pi over n radians counterclockwise, and a reflection about a line. This line has slope tangent 2 pi over n. Just a rotation r and a reflection s. Third, these two symmetries have a couple of properties. First, If I were to take the rotation and do it n times, I would get back to where I started from. Second, if I were to take the reflection and do it twice, I would get back to where I started from. And third, there's this strange statement here about the commutator of these two elements r and s being equal to r squared. So if I were to go r, s, r inverse, s inverse, that would just be the same thing. It's just rotating counterclockwise, not by 2 pi over n, but actually by 4 pi over n. Now, if you don't feel comfortable with all of this abstraction, there is a way we can write this very explicitly using matrices. As before, let's let A be the vertices of this regular polygon having n vertices. Here's a picture of what our regular n-gons would look like for smaller cases of n. Our two generators will be r and s, where r now is a rotation that would send p1 to p2 to p3, so on and so forth. What s would do, on the other hand, is it will be a reflection that fixes the point p1. It then sends p2 to pn. It sends p3 to pn minus 2, and so on and so forth. There is another way you can write all of this by using this matrix notation. Here on the left, you can see the matrix R, which is simply a rotation. And on the right here, you can see the matrix S, which is a reflection. We hope that this makes sense. Thanks for watching.